Okay, so when we were last together on Friday, also without the screen, we had been talking about the actual numerical calculation of electron density maps or of structure factors from a known structural model or a given electron density map. And so this is what we had looked at briefly. So the way the computer does things for us is actually do a three-dimensional summation. We've got a set of structure factors, amplitude and phases. Maybe they're only approximate, but we assume at this point that we have such a thing. Amplitudes from a set of measurements, phases from some at least approximately correct model. So the computer then does the three-dimensional summation over this set of structure factors, each one multiplied by the appropriate transform kernel. And so we have P, Q, and R just indexing the points on this three-dimensional grid. The grid divisions, or the coordinates at any point on the grid, is equal to the grid index divided by the number of intervals in that given direction. And the intervals are the unit cell length, A over nx, B over n1, and so on. And we said we observe the dictum of the Shannon sampling criterion, that there's no point in us calculating more electron density points than are dictated by the Shannon condition, that the minimum d-spacing sets a limit. We don't need to go to higher and higher HKLs to get smaller and smaller d-spacings, and vice versa when we come to calculating structure factors from a given density, as indicated here. So the way we calculate structure factors, the in general complex valued ones, is to calculate first the real part, A, so the general amplitude and phase expression, exponential expression for the structure factor. Of course, we can apply the Euler transform, the Euler relationship, and have the real part and the imaginary part. So we compute first the real part as a three-dimensional sum over these grid points, and then similarly the imaginary coefficient B as a three-dimensional sum. We can combine those to get the amplitude by saying that the amplitude is the sum of the squares of the real and imaginary coefficients, and the phase corresponding is the arctangent of the ratio of the imaginary part to the real part. So that's numerically how we get structure factors from a density, and as on the previous slide, how we get a density from a set of structure factors. And here, again, the Shannon sampling criterion that we talked about a bit on Friday. And the other thing I mentioned on Friday is that there is this technique, method called fast Fourier transformation, which allows economies in computing time for computing either the density, as indicated up here at the top of this hard-to-read slide. So we can compute a density or the structure factors by this fast Fourier transform technique. And the underlying principle is, okay, so let's say in this top part we're calculating a density. For simplicity in explaining this or showing this, we consider just a one-dimensional density. So it would be a summation over the H00 reflections. That would be a projection of all the density onto the x-axis. but we don't want to be messing up this slide with all kinds of three-dimensional summations. The principle is the same for 3 dimensions or 2 dimensions as for 1. So if we have this summation over a certain number of grid points, so we have n sub h grid points that run from 0 to n sub h minus 1 or nx minus 1, okay? And that sum can, of course, be broken up into a pair of sums of even order and odd order terms. So we can sum over all of the even valued HOO, that is f of 2h00, and over odds, f of 2h plus 1, 0, 0. So we split this n-dimensional sum into 2 sums of dimension about a half n. And what we notice there is that when we compute each of these sums, because of the appearance of this 2h plus 1 and so on, we in each case have to evaluate this quantity, which comes out to be 1 over a times this complex exponential. That comes out of this expression. And then what we're left with is an exponent in each of the sums, which is of the same form. Minus 2 pi I even h times x, 2 pi I even h times x. So once we compute this quantity for a given value of h and x, we compute it once, we can use it twice. Okay, so there's a savings of half. Similarly, if we're trying to compute the structure factors from the density, we again have an n-dimensional, a one-dimensional sum over n terms. We can again split that sum into 2 over even orders and over odd orders. This plus 1 part of it comes outside of this second sum, so we just have that multiplying the second sum, this one term. But the even, the exponent here, 2 pi I h even divided by n, again, we compute it once, but we can use it twice. And then you can continue. Each of these 2 sums can be subdivided and make an additional savings of computing an exponential function once, but using it twice, or now like 4 times, and so on. And it doesn't have to be just, let me not get ahead of myself. All right, so here in words is the principle. We subdivide the sum of n terms into separate even and odd order terms, then sum each of those can be divided into further subdivision. The net effect of the economies in the evaluations of these exponential functions is a reduction in the size of the calculation for if we have n data points. If we didn't do this divide and conquer approach, we would have a calculation of order n squared. But when we do the divide and order count approach, we reduce that from n squared to n log n. And as n is large, that's a big saving. When n is large, that's a big saving. We could do this by dividing into 3 sub-sums, right? With indices 3n, 3n plus 1, and 3n plus 2, depending on the factors of n, the number of subdivisions. So this became a practical and important and valuable technique when Cooley and Tukey applied this approach to using digital electronic computers. Although, in fact, the divide and conquer approach had been discovered by Gauss, right? But if you're doing all this by hand calculation, in the size of calculations that we're concerned with in macromolecular crystallography, or even in small molecule crystallography, is impractical without computers. So although Gauss had discovered it in the middle of the, in about the turn of the century, around 1800, it was not practically useful at the time because you needed fast computers. So here's a look at the kinds of savings. We're tabulating numbers of grid points, and if we list them as powers of 2 to the 0 to the 1, and so on, down here to 2 to the 15th, then the square of those numbers are these. By the time you square 2 to the 15th, you get this very big number, which is about 1 billion, on the order of 1 billion. But if we look at just the n log 2, which is the order of the order the calculation becomes when we do the divide and conquer, that what was 1 billion operations to be computed is now reduced to 500,000. So it's a big saving, and the savings is more important the larger the number of grid points, or the finer the grid. The finer the grid, or the larger the data set. So this is going on in the computers too, okay? So those three-dimensional sums are computed by the fast Fourier transform algorithms. And furthermore, another important contribution to this FFT approach in crystallography was made by a guy out at Scripps, I think he is, right? Or is he at the University in San Diego? I can't remember. By the name of Lynn Tenite, a Dutch, well, it's a Dutch name, he's an American guy. And what he realized was that in crystallographic calculations, we can use symmetry to an advantage to further reduce the number of computational operations needed, so that the FFT algorithm can be made even more efficient if one incorporates symmetry properties depending on the space group of the crystal of concern. We also mentioned on Friday, I think, that we can see both the density, electron density distribution, and the set of structure factors as atomic summations. Clearly, the electron density is a sum over the atoms of the unit cell, each atom represented by its own electron density at its particular position in the unit cell. And that, it turns out, is equal to the sum of products of the atomic electron density, so with the nucleus as orange, and then this delta function, which positions each of those atomic densities at the appropriate place in the unit cell. So we have an atomic summation to get the density. But similarly, we can have an atomic summation to get the structure factors. We say, okay, the structure factor is the Fourier transform of this sum over the atoms. Not the sum over the HKLs at this point. We're not doing a Fourier summation. We're just doing a summation over these atoms, each appropriately positioned. And the Fourier transform of a sum is the sum of the Fourier transforms. That's an interesting and valuable property of Fourier transformation. And it doesn't matter whether we're going from densities to structure factors or the other way around. But still, all Fourier transforms have that property, that the Fourier transform of a sum is the sum of the Fourier transforms. And if we replace now this atomic density in here by this formulation, the local atomic density, but then positioned by the delta function to each to its appropriate place in the cell. So then it turns out that the Fourier transform of this kind of a function, a product of functions, this is called a convolution product. Right? So the Fourier transform of a convolution product is the product of the Fourier transforms. So we can have the Fourier transform of each individual atomic density, and then the Fourier transform of this array of delta functions. We may find time to talk further about the properties of the delta function a little later on, but I don't want to take the time to do it now because we're behind where I had hoped we'd be at this point, and we're going to lose another class or so. But the point is, there is this property of Fourier transforms, that the Fourier transform of a convolution product is the product of the Fourier transform. So the Fourier transform of an atomic density is the atomic scattering factor. This is the way we kind of lump all the, bring together all the scattering power of the Z electrons in an atom to get a composite scattering factor. We don't have to consider the electrons one at a time. And in fact, we can't do that because we know that the electrons are not particles that we can count and work with separately. It's a probability density distribution. The electron density is a probability density. And then the Fourier transform of this delta product, this delta function, it turns out is this simple imaginary exponential. That's a property you wouldn't know off the top of your head. We'll try to develop it perhaps later on. But it is so. So if we have these two Fourier transforms, then we can go from there to, in fact, the structure factor, which is also obtainable as the atomic summation. So both the structure factor and the density have an atomic summation representation. No, let's not begin talking about the delta function now. We'll take the rest of the hour, fascinating as it is, but we need to move on to the next topic about scattering of X-rays by electrons and atoms and molecules. So, there. Okay. So back when we were talking about the wave nature of X-rays and electromagnetic waves in general, we saw that electromagnetic waves, or pulses, result from the acceleration of a charged particle. So here we have a simple diagram where we have a point charge Q that is accelerated. Let's call that acceleration direction the Z direction, and then we have an orthogonal for simplicity in thinking. We have a Cartesian coordinate set there. So the result that was deduced by J.J. Thomson, who is the discoverer of the electron, and by the way, it's pretty straightforward derivation, and it is presented in those X-ray diffraction physics notes that I said are out there on the FTP site. It's about 100 pages of notes, but there are maybe 20 pages related to this subject, which I think explain things in a bit more detail, and I hope more clearly than we can do in these sessions together. But the result is that the electric field vector resulting from this charge acceleration is equal to the negative of the amount of that charge divided by the square of the velocity of light, and the distance away from the charge that we're observing. So we can be considering observing these effects in any position all around that charged particle or that origin. And so at some distance, in some direction, the electric field is given by this cross product of a cross product. The point is that the electric field is given, the magnitude of the electric field is given by the component of the acceleration that is perpendicular to the direction of observation. So in vector terms, it's that. In just magnitude terms, it's that q over c squared r, just as here, times the separation of the acceleration times the sine of that angle between the acceleration direction and the observation direction. So it's quite a simple calculation for any given point at any distance r in any particular direction from the origin. And the negative sign, it means that the electric field vector is opposite the perpendicular component of the acceleration vector. So this was as deduced by J.J. Thomson. And it had earlier been deduced from the Maxwell equations that this business of accelerated charge producing electromagnetic radiation, we don't know of any other way for electromagnetic radiation to be produced, except if we get into the mysteries of nuclear physics. Okay, so we want to apply that result. We want to apply this result for the electric field for an due to an accelerated charge to the scattering of X-rays by a free electron. So the electron gets accelerated by the sinusoidal oscillation of this Coulombic force. The force on the electron that the electron experiences is equal to its charge times that electric field vector. So the charge is a scalar, not a vector. So we have this Coulombic component, QE, right? And in our case, the Q we're worried about is the charge on the electron, which we generally symbolize as E, and it's a negative charge. Right? There's magnitude E, the charge of an electron, and it's a negative charge. And then this electric field is an oscillating one, because we're talking about the electron's motion being driven by an incoming electromagnetic radiation wave. Okay, so here is an expression for the X-ray plane wave incident on the electron, which we can, of course, rewrite as the cosine omega t plus I sine omega t, either as the imaginary, the complex exponential, or as the cosine plus I sine number. Well, that force on the electron, coming as a result of the electromagnetic radiation oscillation, of the input, the incident X-ray electric field oscillation, that has to equal the conventional second law of force from Newton's equation, F equal ma. Right? So we have the mass of the electron, and the acceleration is the second derivative of the distance, or the displacement, with respect to time. So we say that ma equals qe, and then make these substitutions. The electron mass, this plane wave representation for the incident electrons, solve for the acceleration, and we get this result. And if we take all of this pre-exponential factor and call it a naught, a sub 0, so we say that a is equal to a sub 0 e to the I omega t, just like here, e was equal to e0 plus times e to the I omega t. So if we are writing for a0 in this way, it just comes from this collection of factors. Now we apply this Thomson equation for the radiation from an accelerated charge, right? Just as we looked at on the preceding slide. So what we get then is that the the amplitude for the scattered X-rays. So what we do in these discussions and also in the notes, we use a Roman E to represent the incident wave and the script E, the electric field of the incident wave, and the script E to represent the electric field component of the scattered wave. So the scattered wave has amplitude given by this, just falling out of these equations, making the appropriate substitution, and then simplifying a bit, we get E squared over mc squared times the electric field amplitude divided by the distance at which we're observing the field. Okay? So this is the amplitude of the scattered wave. The amplitude at R in the equatorial plane perpendicular to the polarization direction of the incident X-rays. That is the electric field oscillating this way or in between, or is there a mixture of polarizations? Okay, X-ray scattering by a free electron at rest has this amplitude, which we notice, again, after all of this cancellation of negative signs here, we have a product of three of them, right? The charge on the electron here, and then this negative sign, which is coming from the fact that this amplitude of the oscillation and the electric field are anti-parallel. So it comes down to this relatively simple looking result. So the amplitude is, the amplitude of the scattering, the scattered amplitude is weaker the farther away we are to observe it. So it's diminishing with time because we're talking about a spherical propagation. So the constant factor is this one that's symbolized R sub E. Right? It's this collection of elementary constants, E squared over mc squared, mass of the electron times the square of the velocity of light. And this summarizes it a bit more succinctly. The basic principle is we have to equate the Coulombic force with the Newtonian mechanical force, dynamic force, okay? QE equal MA, where the incident wave is E naught e to the I omega t, solve for the acceleration, substituted in the expression for the scattered wave amplitude, and so this is just repeating what was on the previous slide. Now this collection of constants, E squared over mc squared, is called the Thomson scattering length for the electron. In honor of Thomson, who figured much of this out at the very beginning, in the first place discovered the electron. So here, restating it in the following way, and noticing that this thing we call the Thomson scattering length for the electron, well, it is a length if we look at the dimensional analysis. We have E squared, that is the square of a charge, divided by a mass, by the square of a velocity. So if you start going through those dimensions, you end up, it's the square of charge over mass times the square of distance divided by the square of time. That comes down to a force, right, divided by mass times the inverse square of time. That's an acceleration divided by the inverse square of time, which is a distance. So this collection of constants has the dimension of distance and has come to be called, I guess almost from the very beginning, the classical electron radius, the radius of the classical electron. And how that comes about, so that's the quantity, E squared over mc squared, the Thomson scattering length for an electron. The notion of the classical electron radius, because, of course, at the time Thomson was talking about all of this, the Schrödinger equation and Heisenberg's approach to the quantum mechanics were very new things, and still much up in the air. So if you consider first the electrostatic potential energy that would be required to bring little elements of charge from infinity to within this sphere of radius r sub e. That gives us an electrostatic potential energy, E. E is not amplitude here, it's energy. Is charge squared over the radius of the electron. And if we consider next the relativistic mass energy of the electron, mc squared, and if we equate these two, we solve for the electron radius and get our quantity E squared over mc squared for Thomson scattering length. So the Thomson scattering length is also called the classical electron radius. For historical reasons, we now, on the basis of quantum mechanics, know much more about electrons than was presented in this very classical picture of point charge. Okay, so that's the scattering by a free electron. Free electron either at rest or in motion with non-relativistic velocity. Now, the other thing to think about for a moment is this notion of the phase reversal. That is, the electric vector of the scattered radiation is opposite, is anti-parallel to the perpendicular component of the charge acceleration. So if we think of an incident sinusoidal wave, okay, here looking like a cosine wave, mapped as a cosine wave. So here's the variation of the amplitude of the incoming wave. What about the acceleration that that incoming wave produces when it forces the electron to oscillate? Well, that acceleration follows the force. So the range of the charge acceleration is from plus to minus. By the way, the vertical, these are all drawn on the same vertical scale, but it varies from one set of these wave diagrams to the next. Okay, so the acceleration follows the incident wave. So the phase of the acceleration is equal to the phase of the incoming wave. Now, what about the motion of the charge, the electron that's being subjected to this incoming wave? Well, if the acceleration is at its maximum, or the electric field is at its maximum, what would be the displacement? Well, at the top here, the motion has stopped because it was coming up, and it still has to go down. So at the maximum, it's 0. So the charge displacement, the motion of that electron being tickled by the incident wave, is pi over 2 behind, 90 degrees behind the phase of the acceleration or the incoming wave. Okay? So that's the phase of this oscillatory motion that's imposed on the electron. Well, what about the scattered wave? How does that relate? Well, the scattered wave, we know, is going to have phase opposite the incident wave. So that's another 90 degrees or pi over 2 phase shift with respect to the motion of the electron, the forced motion of the electron. So that the net effect is we have a pi phase shift. The scattered wave is pi shifted from the incident wave. that appears as a negative sign in that expression for the electric vector in terms of the charge and acceleration. It's the same diagram line. So we talked a little bit about the notion of polarization. What do we mean by polarization? Well, polarization has to do with how is the electric vector in the incident wave oscillating? Is it all oscillating along this, is all the oscillation along this direction that we've conventionally called x, or all along this direction that we've conventionally called y? So do we have linear polarization along x or linear polarization along y? Or is it someplace intermediate? Or is there a non-polarized incident beam, so that we have many of these components, E naught, with components x and y? So the incoming wave tickles the electron, which scatters radiation or passes it by. But the point is we change the phase, opposite phase here for the scattered beam to the incident beam. Opposite phase along x, opposite phase along y. And then if we allow for the fact that the scattering, considering just for now, just scattering in the plane of x and of x and z or y and z. So the scattered beam would then have to be adjusted, the y component of the scattered beam would have to be adjusted by the cosine of 2 theta, the scattering angle. So that the scattered beam, we could always resolve its polarization into the polarization along x and y, the y part adjusted by the cosine of theta. So x squared plus y squared, cosine squared of 2 theta, giving the squared polarization of this scattered beam. And similarly here, the cosine 2 theta part of it doesn't enter in, so the unscattered beam, the transmitted beam, just has components e squared x and e squared y. So along with figuring out the amplitude of the scattered electric vector, Thomson had worked through, in this classical way, the polarization phenomena as well. So here we can see that any particular direction of polarization can always be resolved into its pair of components, x and y. And if this has unit amplitude, then these components go as square root of 2 over 2, just by right triangle construction. Isosceles right triangle. Okay, so now let's consider this. How is this going to look? If we have incoming radiation hitting our electron, its vertical component is going to set the electron into this kind of motion, so the transmitted beam will also have the vertical oscillation. But normal to that, along the y direction, we would have also a vertical component, and off in some general direction, of course, the cosine 2 theta factor would reduce this amplitude. So the scattered beam, except in this equatorial plane, the scattered beam would have a different amplitude than the incident beam. Okay, if we look the other way around, here for horizontal polarization, then what is it going to do? Well, the transmitted beam still the same. Up here, we still have this same oscillation along y, but now we got this, in the general direction, we have this, this is intended to be a sinusoidal wave, not so easy to see, but this kind of thing, but with respect to the other polarization. And if the beam is unpolarized, then we have this going on all around the axis of the incident beam, the direction of the incident beam. And so for the beam that we would get upstairs from the rotating anode or sealed tube anode, this is the case. We have pretty much unpolarized electromagnetic radiation. So all of these directions of polarization would be components of the incident beam on the electron. And if we have those unpolarized beam incident on the electron, you can see that this is a way to think about this disturbance of the electron, the wave that is set up having this three-dimensionality. Right? We're propagating this wave spherically. It's not just a wave in one or another plane. It's a component, and depending on the circumstance that the electron's in, whether it's an electron in an atom or electron in an atom surrounded by other atoms, its freedom to oscillate may not be the same in all directions. There might be some stiffer springs, stronger restoring forces for an anisotropic environment for an electron or an atom that we're considering. Oh, and so those are just these imaginary constructions of models for this three-dimensional oscillation. So it's not like a water wave where we just have, not like a water surface wave, it's a three-dimensional wave effect. Oh. Ah, okay. So, 3:30 in the afternoon, maybe not good. The amplitude, as we said, depends on the angle of scattering. So here we're considering the primary beam and the transmitted beam. And here we're considering scattering in these various directions. So what is happening then to this more or less horizontal component of the polarization, depending on 2 theta? So if we get to 2 theta of 90 degrees, then we're back to here, square root of 2 over 2. That's the strongest beam, depending on the polarization direction. But in between, we will have to multiply by the cosine of 2 theta. Here's this value of 2 theta, here's this value of 2 theta. But what's the cosine of 2 theta? 90 degrees, well, that's 1. As is the cosine of 0. So there's a lot going on to try to imagine in this scattering phenomenon. Okay, so now let's consider, what if this is not a free electron? What if it's an electron in an atom? Just we're considering one atomic electron. It could be a one electron atom like hydrogen, or it could be one electron in the uranium atom. What we want to consider an electron that is bound in an atom. That is, it's got an interaction with the nucleus. There's electrostatic interaction between the positive nucleus and this electron, or between the positive nucleus and this electron of interest and all the other electrons too, which in effect weaken the effect of the positive charge of the nucleus. They kind of screen our electron of interest because they're interacting also with the nucleus. But anyhow, a bound electron. What's the situation there? Well, we have to be worried about the Coulombic force again. So this is the driving force, the incident electromagnetic wave, and it's a Coulombic force of the form QE. But since it's a bound electron now, there's a Hooke's law component, that as the electron gets farther from the nucleus, it would want to be restored. If it gets closer to the nucleus, be held more tight, and so on. So there's a spring constant to worry about, kx, where x is the position of the electron. And then these two forces, the Hooke's law force, the Coulombic force, they add together, they're of the same sign, and they must balance the Newton force, Ma. Well, this differential equation has a solution of the form x naught e to the I, solving for x here, the differential equation. It has a solution x naught e to the I omega. So now we consider, well, what about the velocity of the electron under these conditions of motion? Well, we have to differentiate the displacement of the electron from its mean position, say. Then we get x naught I to the omega t again, because no matter how many times you differentiate these exponential functions, you keep getting them back. But now we have to differentiate what's in the exponent itself, not the exponential function, but its exponent itself. So we get this factor I omega, then multiplies the displacement function. And to get the acceleration that that electron, now being tickled by the incident beam, is experiencing or undergoes, we have to differentiate again, differentiate the velocity with respect to time, okay? And that gives us negative omega square, so omega square because we differentiate omega out of the exponent again. We get another factor of I, so we have I square omega square. Well, I squared is -1. So the acceleration then has this. So if we put that in for the acceleration here, and we put this in for the displacement, and we have this for the incoming radiation, so the equation of motion reduces to this, where we can just drop out the e to the I omega t factors because they appear everywhere, and in fact, we can factor them out. So that the displacement then gets expressed in terms of the electric field of the incoming radiation, the frequency of that radiation, this force constant, this elastic force constant, restoring force constant, and the mass of the electron. Making those substitutions and carrying it through the algebra, we get down to this. We can define this ratio k over m as, call that, its square root, call that omega 0. Okay, so we have the frequency of the radiation and a natural frequency for the oscillating electron, depending on this restoring force constant and the mass of the electron. Making those substitutions, the acceleration expression comes to this, and putting that acceleration into our Thomson equation for the electric vector of the scattered radiation, how it depends on the incident radiation, and these other concerns, we come again to the Thomson scattering length for the electron, and then this form, with omega, the square of omega, over the difference between the square of omega and the natural frequency of, depending on the mass and force constant. Typically, in all the experiments that are sensible with in crystallography, macromolecular crystallography in particular, the frequency of the radiation, omega, without a subscript, greatly exceeds the natural frequency for the electron oscillation in an atom. Right? Now, the oscillations of the electron will be different for different electrons in the atom because they're experiencing different restoring forces, different strength of interaction with the nucleus, different spring constants in that three-dimensional oscillator mechanical model. Okay, so this just elaborates on the scattering by a free electron by introducing the Hooke's law component due to the interaction between the nucleus, or the nucleus as screened by the other electron, and our electron of interest. Now you have to take it one step further, because if we look at this expression for the scattering by a bound electron, what I said that normally the frequency of the radiation greatly exceeds the natural frequency of the electron of interest. But if by hook or by crook or by chance we are using radiation of a frequency that matches the natural frequency of the electron oscillator, the dipole oscillator, nucleus electron dipole oscillator, then this thing would go infinite, right? How do we prevent that from happening? Suppose we're scanning over a range of frequencies, and there's a particular one that we can match for some particular electron in the atom. Well, that's resolved by the fact that the oscillation of the electron is producing radiation, electromagnetic radiation. So there's an energy loss, a radiation loss, that's equivalent to a damping force on the oscillations of the electron. So it doesn't, that ratio doesn't go infinite. Right? We introduce another term in the differential equation. There we go. We introduce another term in the differential equation. A typical damping force is proportional to the velocity of the oscillating particle. So it too has an associated force constant, or damping force constant. So we have the restoring force constant and the damping force constant. The restoring force constant was defined in terms of the mass and the natural frequency for that nucleus electron dipole oscillator, and the damping constant is we can define that as proportional to the mass, and this quantity we'll define as gamma for the moment. And when we go through considering the solution of now this a lot more elaborated differential equation of motion for this electron under the influence of the incoming radiation and experiencing its attraction to the nucleus and being damped by the loss of the radiation it's emitting. Well, again, a differential equation of this form has a solution of this form, x naught equals the I omega t. When we go through the same kinds of steps as on the previous slide, what we come down to realizing is that x naught is E, charge on the electron, electric field amplitude divided by mass, and then this expression in terms of the frequencies. What we had before was without this minus I gamma omega. What happens here is that the result of, as a result of the restoring, as a result of the damping force, we introduce this quantity I gamma omega. So when the radiation frequency matches a natural frequency for the nucleus electron dipole oscillation, we get then a complex value amplitude of oscillation. And when we make those substitutions, just as in other steps before, what we get down to is a result that the scattered radiation, the amplitude of the scattered radiation, again involves this amplitude for free electron scattering, but then modulated by this complex valued quotient of frequencies, the radiation frequency and the natural oscillator frequency. So if and so this then, the combined effect is the scattered wave amplitude in the case that the frequency is near to or matches exactly, well, is near to the natural vibration frequency. And the scattering factor then is defined as the amplitude of the scattered radiation from this bound electron in the subject to the effects of the nucleus attraction and the damping force, divided by the amplitude of scattering by a free electron. That turns out to be all of this here. This is the amplitude of scattering from a free electron. So all of this part of it, with the fundamental constants and so on, falls out, and we're just left with this frequency ratio, in general complex value. Well, we can rewrite that as 1 over 1 minus this ratio, omega naught to omega, the square of that, and then also I gamma over omega. If generally gamma is so small, is often so small that we can neglect this, and we're just left with this 1 over 1 minus the frequency, the square of the frequency ratio. If we don't have the restoring force to worry about, the scattering for the free electron, defined in this way, if we say E0 free over E0 free, that is a unit value for the scattering factor for a single electron in the absence of these other effects. So for a free electron, no restoring force, and if we're at a frequency far from a natural, there is no dipole oscillation, so this part goes away, and the scattering factor for a free electron has value unity, because we're taking it as the ratio to the free electron scattering, which is this business, this lump of constants plus the amplitude of the incoming radiation, times the amplitude of the incoming radiation, divided by the distance at which we're making our observation. So this relates to what I was saying at the last. Oh, yes, we're over our time. Okay, so we'll conclude here, but let me just say, this comes down to the expression for the amplitude of scattering in which we consider the effects of the nuclear attraction and the damping force on oscillation. Okay, so this is the more general formula for the amplitude of the scattered radiation. If we divide that by the amplitude for the scattering by a free electron, we get this frequencies ratio, as we saw here. And if gamma is much less than omega, which often it is, then this comes down to this expression, 1 over 1 minus the square of the frequency ratio. And if we're in the high frequency limit, where the natural frequency is much less than the radiation frequency, then this ratio becomes very small, and we're at a unit value for the electron scattering factor in what we call the high frequency limit. So if there's no damping, it simplifies to this. If there's if it's far from any natural absorption frequency, it reduces to. So a free electron at rest has scattering factor 1. So under these conditions of undamped oscillation at very high frequencies, it is as if the scattering factor for a bound atomic electron is about the same as the scattering by a free electron at rest. Okay, I ran over time, so let's say that's enough for today.
Is that what is omega, the incoming frequency? Is that?
That's without subscript. That's omega.
Is that in our biomolecular experiments? Is that the case where the X-ray radiation frequency is much, much greater than
the natural frequency for the nucleus electron dipole oscillation? Yes, but
The important exception is the case where your biomolecular crystal contains some heavy atom, like a mercury or a lead or a uranium that's in there as a marker for trying to get a handle on the phases. And then the difference is not, well, the difference is small. It's not zero, but it's small. And that gives then rise to absorption effects, absorption of incoming radiation by that heavy atom, and anomalous scattering, which is a great tool for getting at experimental values for the phases.
Isn't the reason that the scattering factor intensity would be decreased because of this reason? If you add like heavy atoms,
No.
the scattering factor intensities.
Let's say you add heavy, well, first of all, you generally add only a few heavy atoms, okay? They only go to a selected number of places. But you're thereby, in effect, increasing the total scattering power because those heavy atoms are strong scatterers.
Right.
But they often bind in only partially, so they're in a site maybe a uranium atom binds maybe only half the time or a third of the time. So it's like a weakened or a smaller uranium atom. And furthermore, there can be not only partial occupancy but disorder. So it typically happens that the scattering from those guys falls off. But it's following along pretty much the scattering by all the other stuff. It still is a big component of the scattering. Getting at the fall off of scattering is where we're going next with this. We'll be looking at the shapes of the atomic scattering factors, how the atomic scattering factors decrease with scattering angle. That's actually the next topic for Wednesday.